It's a great pleasure to be here. I mean, I didn't have to make a long journey because I'm Jay's more or less next door neighbor, and have been such for the last like 26 years, more or less, 25. Yeah, quite long. You know, he's delicate as usual, and it's been a pleasure, a real pleasure. Actually, I published one paper with Jay and with our students, Odette Ben-David and Michael Asaf. It was a sort of joint venture of theory and experiment on a mechanical instability. It was like about 10 years ago. It was about Faraday waves excited by chirp frequency. Lazar Friedland will be giving a talk about what we call autoresonance, and maybe he will mention it, maybe he will not. But it was an interesting project. It made into PRL, but you know, it was 10 years ago, and you know, my memory is not that long. So I'll be talking about different subjects. We discussed yesterday what should be, you know, proper subjects for this fest, and of course, you know, people who talk about things that more or less Jay does too. It's obviously appropriate subjects. And then topics, somebody said that no, topics that we are sure Jay will be interested to hear about. It's also appropriate subject. So I'm not sure that this one belongs to these two, so I immediately suggested another sort of an additional criterion. That's a subject that the speaker thinks that Jay must know something about. Anyway, I'll be talking about large fluctuations in several non-equilibrium systems, several types of non-equilibrium systems. And actually what I mean by large fluctuations, what I need to qualify it. I'm talking about large fluctuations in macroscopic systems where typical fluctuations are small, which immediately means that I'll be talking about unusual, rare events, atypical events. Okay, large fluctuations, large deviations of several kinds. And why should we care about something that we know in advance that this something is rare? Well, obviously, an immediate answer is that these rare events can have major or even dramatic or sometimes tragic consequences. And it's like earthquakes or volcano eruptions, market crashes, extinctions of long-lived, well-established species, power grid failures, and things like that. Something that you don't expect to happen on sort of a usual intuitive time scale, but when they happen, they have dramatic consequences. And these, of course, are bad large fluctuations. But there are also good large fluctuations. And one of them is present here. His arrival to the Hebrew University, and of course, not only his arrival, but also the achievements and the spirit of great science, and you know, strong desire to look beyond what other people have looked at in important systems. What it caused is essentially it caused a nucleation. You know, nucleation comes from a relatively rare event. So it was a nucleation. As a result, the nonlinear physics direction that had started to develop a few years before he came, actually, this nucleation essentially helped or was a decisive factor in creating a nonlinear sort of physics department, micro department, which now includes two flourishing experimental groups and 4 theoretical groups. And this wouldn't have been possible without his arrival, because, you know, before that time, there was like 1.5 theorists working in this direction, and nobody takes theorists very seriously. And I can now have like a few years before retirement, so I can say that it's a correct point of view. But yeah, so his arrival essentially made it. Now let's speak about large fluctuations, which are in some sense simpler to understand. there is an intrinsic fundamental reason behind our sort of desire to understand them. It is because in equilibrium, we don't care much whether the fluctuation is large or small. We can quantitatively understand these fluctuations just using, if it is a classical system, macroscopic system, just using Boltzmann-Gibbs distribution. So if it is a very rare event, for example, what is the probability that one half of this room becomes a void and all the molecules go to the other side? This is a pathetically unrealistic event, but we can calculate it on the back of the envelope just using knowing the free energy of an ideal gas and just computing the Boltzmannian exponent of it. Okay, so we have a complete control, quantitative control of fluctuations, whether they are small or large, if the system is in equilibrium. The moment the system comes out of equilibrium, it's a new world. Okay, and we don't have anything even distantly resembling this robust and universal principle like the Boltzmann-Gibbs statistics. I'm talking about the classical physics, but the same kind of questions, of course, can be generalized immediately into the quantum realm. So these large deviations, as a result, are a good test of our understanding or the lack of non-equilibrium physics. So as a result, large deviations have been the focus of a relatively big community of statistical physicists, mathematical physicists, probabilists that came together and described more or less the same thing using a different language. Okay. So I'll briefly mention two classes of systems that participated in developing in the recent years, and then I'll talk a little bit more about the third system, non-equilibrium surface growth, but I'll start with the diffusive lattice gases. So this is sort of the simplest models where this stochasticity, where the randomness is already intrinsic, and still they're not easy to understand quantitatively if we really want to understand them well, including large fluctuations in such a system. So I'll start with the SEP. SEP is a simple symmetric exclusion process. Let's start with one dimension. We have a one-dimensional lattice, and at each side of the lattice, on each side of the lattice, there can be a particle or no particles at all. And you cannot have more than one particle on a single side of the lattice. So this is exclusion. Now, what is the dynamics? You pick up a particle at random, and like in a random walk of independent particles, it moves either to the right, hops to the next side, or hops to the left with the same probability. If the target site is vacant, if it is occupied, you do nothing. You pick up the next particle and you do the same game. That's it. Okay, simple symmetric exclusion process. The other model that I can mention here is the so-called KMP, Kipnis-Marchoro-Prisutti model. This model was invented about 30 years ago by mathematicians, mathematical physicists, who wanted to understand quantitatively how the Fourier law of heat conduction, that the heat flux is proportional to the temperature gradient, how it arrives rigorously in a simple stochastic model. In a model where the stochasticity is already intrinsic, where you have n particles, and how these things arrive in the limit of n going to infinity. Okay, so here the model is the following. Nobody moves. Here there are some agents, which I mark here by these arrows, and each agent has some number to it. Just think about its height. And the rule of the game, and it's of course it's a continuous number. It's a positive or non-negative real number. And then you take two guys, two neighbors, and they collectivize their sort of heights or their energies. People call it usually energies, and then they redistribute these energies among themselves according to a simple law, usually uniform distribution. So this guy, for example, and this guy added the energies, and then redistributed it randomly. So it's not exactly socialism, because socialism usually redistributes it in a sort of well-planned sort of maybe even well-intended manner, but it's a different story. I can talk about it very long, but I should stop myself. So just redistribute it randomly. And now if you put this guy in contact with a thermal bed, so that for example its energy is fixed by a thermal bed, and this one on the left is fixed by another thermal bed, so now you have a non-equilibrium. They have sort of randomized the energy, but there is a sort of a systematic trend. So this was exactly the point, to prove mathematically rigorously the Fourier's law, and it was proved, just at the level of theorems. But then this model continued to play an important role. I mean, here you can ask the same question as a very similar question, but in the context of particle diffusion rather than heat diffusion. But let me go to it very shortly. So yes. So the simplest non-equilibrium setting is, as I said, two reservoirs or two thermostats with different densities of temperature. In the context of the SEP, of the simple symmetric exclusion process, you just, let's say, dictate that this point is always occupied, or it's a little bit more complicated. You introduce a microscopic rule of injecting the particles and taking the particles out here and here, so that at the macroscopic level, this corresponds to prescribing a constant density here and a different constant density here. So what would happen? What will happen in the system at long times? Well, of course, because the densities are different, you expect an average current to appear through the system. And this average current is essentially the measure of your being out of equilibrium. Because where the reservoirs are identical, there would be no average current. There would be only fluctuations of currents, local fluctuations of current. So you have an average current, and in the SEP and in a bunch of other models, and a broad class of other models like that, which are called diffusive lattice gases, this current is proportional to a function which depends on rho minus rho plus, and it's inversely proportional to L. Now in the SEP, it happens to be that despite the fact that there is an interaction, there is an exclusion interaction, at the level of the averages, at the level of the average current, the SEP behaves as a bunch of independent random walkers. So in this case, this A is just proportional to the difference of the densities. But for other models, it's like the model nonlinear diffusion. This can be a more complicated function. But now we ask about fluctuations. Let's, for example, measure how many particles entered this reservoir, or we can pick up any other point and measure the current through this point at long time. And we can ask ourselves, what are the fluctuations of this current? Okay? And it turns out that the steady state fluctuations of current, this current will steadily fluctuate around this average value. So this will be a statistical steady state, but it will be a non-equilibrium steady state because there is a current that is flowing through the system. So we're asking about the fluctuations of this current, and it turns out that at long times there is a stationary distribution of this current, and it behaves like this. So it's an exponential of some function which depends on the current that you condition on rho minus and rho plus, on some microscopic, on some coefficients that characterize the model, and very importantly, it depends in a universal way on the size of the system. So the longer the system is, the less probable is to see any deviation of the current from the mean, from the average current. So this function actually is 0. This function S is 0 when I plug here this average current. Okay? And all the deviations becomes large fluctuations in the limit of L going to infinity. Become rare event when the L goes to infinity. But a finite large L, this is the structure of the result. And this function S is called the large deviation function. Okay? Now, if you look at it carefully, you see that it resembles the Boltzmann-Gibbs distribution, because this L plays the role of 1 over the temperature of the system, and this guy plays the role of the free energy. okay, of the free energy density of the system, okay? So this, in a sense, it's an immediate generalization of the equilibrium statistical mechanics to a non-equilibrium situation, where if you know how to compute this function, you essentially have an analog of Boltzmann-Gibbs distribution. Another question that you can ask in relation to this question, how to compute this S for a given, for every given deviation of the current from the mean, is what is the most probable configuration of the system? And in this simple system, the only thing that describes a configuration is just the density profile. What should be the density profile, which is different from the expected density profile, which is just a linear slope in the case of the SEP? What should be this configuration of the density, which with the highest probability contributes to a given atypical J? And what happens is that when L is very large, so that any significant deviation of the current from the mean has a very small probability, the problem turns almost deterministic in the sense that there is one certain configuration of the system that gives a dominant contribution to this current, and all other systems are much less probable, or even, well, essentially, so the most probable configuration can be called the least improbable. It is already improbable, but if you are interested in computing this rare event, you really should ignore all others, which means that there is one trajectory of the system, and in this steady state system is just a one configuration that somehow is most responsible for the large deviation, which gives you a hint at a theory that can exploit this special phenomenon. Okay, so these models, lattice gases, they are formulated at the level of microscopic of the agent model, the level of interactions between its elements, some elemental processes. But there is a large scale description which is very convenient and which was developed some 30 years ago, 25, 30 years ago, mostly by Spohn, Herbert Spohn. He's in Munich. And the description is the following. Instead of talking about lattice sites and individual particles, or these agents, these arrows that I showed in the context of the KMP model, you derive a macroscopic equation that if you ignore this term for a moment, is just a nonlinear diffusion equation. For the SEP, it's just a linear diffusion equation, happens to be. So if you're not interested in fluctuations at all, you can derive from the underlying microscopic model this macroscopic equation, and this is essentially what KN and P did first for the KMP model, and in this way they prove the Fourier law of heat conduction. But if you go one order beyond, you get an additional term which is fluctuating. So this term includes a Gaussian noise which is delta correlated in X and T, both in space and in time, and it includes a prefactor which depends on the local density. Okay, the deviation is actually exploits the local thermal equilibrium, an analog of local thermal equilibrium in this simple system, and it is another coefficient that characterizes your lattice gas. So if you have a lattice gas, and if you know what is its diffusivity and its sigma, which is usually called mobility, you have this macroscopic description that takes into account fluctuations. And this is done in the spirit of the theory of Landau and Lifshitz, a fluctuating hydrodynamics of Landau and Lifshitz. So in Landau and Lifshitz fluctuating hydrodynamics, you have a bunch of equations, three conservations laws of fluid mechanics. And in some of them, in the momentum equation and in the energy equation, there are fluctuating terms. Why are the delta correlated in X and T? Is it just a sort of a priori assumption? No, it is not. Because at distances, when this equation becomes correct, becomes quantitatively accurate, and at long times, when this equation becomes quantitatively accurate, the fluctuations that essentially come from the discreteness of the system, from something that has a typical lattice site scale and the hopping time scale, which is also a very short time, viewed from this bird view perspective, these things become delta correlated. So it's the same, again, in the spirit of Landau and Lifshitz, where where things that happen on the mean free path, let's say of a gas or of a liquid, they assume to be delta correlated because the theory is coarse-grained. Okay, so then you use this equation. Well, and some people use some microscopic models, and you can compute this large deviation function. This is what people did about 10, 15 years ago. And so this large deviation function and this steady state problem that I told you about by now is solved for several models. And there were several surprises. Well, not all of them are real surprises, but well, it surprised many people. There are long-range correlations in the sense that what happens here influences quite a lot what happens on the other side of the system. There is a time symmetry of optimal fluctuations that I'll actually talk about a little bit later if I have time. And what is important, so for several models, they found a non-analytical behavior of this large deviation function as you change the current. And this doesn't have any analog in equilibrium statistical mechanics. So it's like a phase transition at the level of large deviation function. So again, you can trace classical phase transitions in equilibrium statistical mechanics by looking at the behavior of the free energy. Okay, and here by looking at sort of weird behavior of the large deviation function, which is an analog of the free energy, you can define a bunch of dynamical phase transitions, what they call phase transitions that look as singularities of different kinds of the large deviation function. So then you can continue, and this is more or less when we entered. What's happening here? When I started working on this field a few years ago, you can ask some time-dependent questions. For example, you start with a well-defined configuration that can even be deterministic. You put some density here on the left half-axis and some density here, and you're just interested to know what current has passed or what the total charge or total mass of particles have passed through this point at long time. Okay? So you essentially compute the difference between the mass of the right half space and its initial value. Both of them are infinite, but the difference is finite, and you define this passing current or passing mass, and then you ask what is its statistics. Okay. First, was it its average? This is a simple exercise for the diffusion equation for the SEP. You just need to solve the diffusion equation with this initial condition. It will develop this ERF-like behavior, and you just compute this quantity, and you see that the expected mass that passed from left to right grows as square root of time. Okay, it's a diffusion behavior. But then you ask, in each realization, in each experiment or Gedanken experiment or simulation that you made, there will be a different current passing by that time. So there will be a distribution around this expected mean. So what is this distribution? Well, this is its structure. Again, it has a structure of the large deviation function. So instead of the length of the constant length of the system L, here you have square root of dt, which makes sense because in an infinite system, the square root of dt plays the role of the effective system length. Beyond the diffusion length, nothing interesting happens. But there is this function, and now this mt is rescaled by square root of dt. And it also depends on the rho minus and rho plus. So what is this large deviation function? And what is the optimal history? Because now it's a transient process. What was the history of the system in terms of its density as a function of t that contributed most to a given mass passed by time t that you condition on? Okay, and here what comes is optimal fluctuation method that I'll tell you a few words about it a little bit later. And this is already these subjects started. Oh no. Okay, it was a spoiler once again. Goes the wrong direction. Okay. So this chain of work started like almost 10 years ago by Bernard Derrida and his PhD student at that time, Antoine Gershenfeld. And then Setomaran and Varadhan did some mathematical work, and then we sort of explored this length. And there are still many unresolved issues here. But now oh my God. Well, this computer is much smarter than some of its owners, and it has actually only one owner. Okay, so the second kind of system that we talk about are noisy reaction fronts. So you just have a front propagating in space, for example, a front of a bacterial colony expanding, or some front of chemical reactions, and this class of problems can also be described at the level of effective and sometimes rigorously derived Langevin type of equation, which has a deterministic part and some noisy part. So the deterministic part of this equation is called the Fisher-Kolmogorov equation, or FKPP equation, and this is a noise term. Now the noise is not conservative anymore. There is no conservation of mass, but this noise depends on the value of the density here. And again, the question is, I mean, without this noisy term, this is a sort of a classical system that sort of was a very popular toy model of pattern formation in its inception in the 80s, and then still some in the 90s. And now if you have some noise acting here, the question is how probable, well, one of the questions is how probable is it to observe a noisy front which propagates faster or much faster or slower or much slower than its deterministic counterpart, than a front that you would have here if you just drop the noise and ignore fluctuations. And okay, so this is the second class of systems, and it's quite challenging to compute this large deviation function. Now the parameter t, just time, plays the role of the extensive parameter, and if t goes to infinity, it's very improbable to see any deviation of the front speed from the mean. But it's very interesting to compute this, and there were some partial successes. We did Derrida and his collaborators did very important work, and then we started working on it a few years ago, and the last paper is with Pavel Sasorov and Bernard Derrida. Yeah, and this so now this was almost a spoiler. Many years ago, when Jay was a PhD student of Victor Steinberg, they published a paper, a PRL, you see it's 87, before this BitNet message of Jay to Professor Sweeney, where they were interested in explaining how turbulence, essentially Rayleigh-Bernard convection, when it starts in one sort of side of the system, how this propagates to the rest of the system. And they noticed that the propagation of the vorticity that is created by the instability, by Rayleigh-Bernard instability, propagation can be described by an amplitude equation, which is very similar to the Fisher-Kolmogorov equation. And as far as the selection of velocity, which was then a very hot topic, the selection of the velocity of the front is concerned, it behaves identically to the FKPP equation. And the selection problem was very non-trivial, and it's very interesting because if you just look for a traveling wave solution of this equation, you have a bunch of solutions, you have a family of solutions. Okay, but in any specific experiment with a fixed initial condition, you will observe only a unique solution. So what is it in the initial condition or in anything else that defines this selection? So essentially, if we go back, time machine and make a miniature system, a nano system, instead of a sort of robust system that they studied, and of course in their system the fluctuations were not as important, we could ask, or if we create, quench disorder and some noise that changes, you know, the behavior of the system, we could ask what is the probability to see a front that arrived a bit too early or was delayed, okay? But there is no time machine, unfortunately. Okay, so and then in the last, what, 5 minutes? No, 5 minutes? I see, so I was a bit too pedagogical, yeah, I understand. Okay, then let me summarize. What I wanted to really tell you about is that what we are doing mostly in the last 2 years, and this is a very celebrated equation named after Kardar, Parisi, and Zhang. It's become a sort of standard model of non-equilibrium statistical mechanics. And now here the non-equilibrium is intrinsic in the equation and not in the boundary conditions or in the transient. And there is a very beautiful experiment by Takeuchi in Japan. And what here, okay, so let me go back to, go to the, well, I didn't know that the time flies so fast. I thought it only flies fast in matters of years, but yeah. So essentially what I didn't have time to tell you about, but maybe it's okay because, you know, you guys are from a different area. So there is a method which is called the optimal fluctuation method. It's not really new, but it's not still widely known. It is an analog of the classical mechanics when it is used to study quantum systems and the quasi-classical limit. So here we take a stochastic system, which is sort of weakly stochastic, okay, and study atypical fluctuations, and we use a technique that is very similar to the WKB approximation. But it's similar but also different because, you know, there is no interference, no square root of -1, as you have in quantum mechanics. So in some sense, this quasi-classical theory is simpler and more robust than WKB in quantum mechanics. So it gives you this optimal trajectory, optimal history, optimal configuration, like you find a classical trajectory in quantum mechanics that gives you the most important contribution to your wave function. So this analogy can be taken very far, and including to the field theories like the ones I talked about, and it's certainly a valuable tool, and we did some pretty good job, I think, with the KPZ equation in the last couple of years. And so at least I hope that I convinced you that large fluctuations are fun, especially some of them. Thank you very much.